So let us look at x1, x2, xn, IID, normal, theta, sigma square, normal mu sigma square. So what I have seen is under the squared error loss function, all the estimators are minimax. But now what I do is I make the condition that sigma square cannot explode. That means it is bounded above by some constant. So my parameter space which I take is mu sigma, which belongs to R. Earlier sigma was taking any value from 0 to infinity. Now I say that sigma only takes value 0 to C. For some known constant C given value. My loss function L theta A is A minus mu whole square. So that is equal to x bar is minimax. So what I need to show? I know that x bar is minimax when my sigma square is a fixed constant. So I try to fix my constant in such a way such that its maximum risk over 0 to C becomes the constant risk of that. So if I take known variance to be C, so let me call this as 0 to C. Open also you consider there is no problem. So I consider my theta naught to be R cross, and for sigma naught I assume only one value, which is C, right? Because that is where, because its variance would be C square by n. So when I look at the maximum variance of sigma square by n 0 to C, that would become C by n, and the conditions of last theorem would be satisfied. So my theta naught is R by C. So that means this is, here only sigma can take only one value C, which is equivalent to saying that sigma is known. That means I don't have to bother about the values of sigma. So what does that mean? Delta naught x is equal to x bar is minimax under theta naught, that we have already proved. All right? Okay, so now what I need to show now? I need to show that maximum risk of, now theta naught is clearly contained in theta. And R theta delta naught is same as C square by n, sorry, sigma square by n for every theta. Yeah, so what is the supremum over theta belonging to theta of R theta delta naught? So supremum over this, sigma square can go only up to C square by n, which is same as supremum over theta belonging to theta naught. That means when my variance was exactly C square, R theta delta naught. What does that mean? This implies that theta naught. So note that what is happening over here is, if I consider a squared error loss function and I don't put any bound on sigma square, then all estimators are minimax and all of them have the supremum risk as infinite. So if I don't want to change the loss function, then to get a reasonable or to meaningful minimax estimators, I need to have a condition that my sigma is bounded above. Other way could be like if I had to make risk of this constant, I could change my loss function to be L theta A to be A minus mu whole square by sigma square. Then x bar is a constant, x bar has a constant risk, which is 1. Now the question is, can I say that it is minimax? So try to do that if I consider my loss function to be A minus mu whole square by sigma square. Can I say that x bar is minimax? Okay. So the only thing is you have to show that either x bar is base with respect to some prior, which possibly will not happen. So can you say that x bar is a limit of a base? Now the only thing is now prior would be on mu and sigma both. So let me not do over here that I'll give you as an assignment problem. So this is possibly the final result which I'll be doing. So this result says if you have an admissible estimator and it has a constant risk, then it is minimax. So an admissible estimator with constant risk is minimax. Now, if your loss function is strictly convex, then an admissible estimator with constant risk is unique minimax. If the loss function is strictly convex, in A for every theta belonging to theta, then an admissible estimator with constant risk is unique minimax. Before I go for a proof of this, let's try to see the consequences of this. Just now I showed that x bar is minimax, and the approach which I followed was I showed that x bar is a limit of base in certain sense, and x bar has a constant risk. I could have shown this directly from here because I've already shown that x bar is admissible. Of course, that itself involved proving that x bar is limit of base in certain sense. I have already shown that x bar is admissible under the square error loss function. It has constant risk provided variance is known. So it would be minimax. So I don't have to do anything. It just follows from the earlier result where I proved that x bar is admissible under the square error loss function. Now square error loss function, note that is a strictly convex function. So if I look at the second result, it says that x bar is the unique minimax estimator in the normal theta 1 kind of a situation or normal theta sigma naught square kind of a situation where sigma naught is known. So very useful result, although simple to prove. So in the normal theta 1 case, I conclude using this result that x bar is the unique minimax estimator. There is no other minimax estimator. So let us try to prove that. So suppose that delta naught is admissible and r theta delta naught is, let us say, C or R naught, a constant for every theta belonging to theta. What I have to show? I have to show that it is minimax. So that means if I look at, so one way is I show that it is not minimax. So on contrary, suppose delta naught is not minimax, then I should show that I get something funny. I'll show that if delta naught is not minimax, then it cannot be admissible also. So what does that mean? If it is not minimax, what does that mean? There exists a delta star such that supremum risk of delta star is smaller than the supremum risk of delta naught. Is less than supremum risk of but R theta delta naught has a constant risk, so its supremum risk is same as R naught. So what do you get? Supremum of R theta delta star, supremum overtaken theta, is always less than R naught. So that means R theta delta star would always be less than R naught for every theta belonging to theta. But R naught is same as R theta delta because R theta delta does not depend on theta. R theta delta naught because it is constant. So this implies that R theta delta star is less than R theta delta naught for every theta belonging to theta. So what does that mean? That means you have estimated delta star whose risk is always strictly smaller than the risk of delta naught for any theta. And that proves that delta naught is inadmissible. So that proves the first part. Now, second part, you have to show that if your loss function is strictly convex, then the constant risk estimator has, then any estimator which has a constant risk is unique minimax. So let delta naught and delta 1 be two estimators such that both are minimax. So that means their supremum risk is same. So that means R naught, which is supremum risk of delta naught, this is also same as the supremum risk of delta 1. Then I should say so that delta naught and delta 1 should be same almost surely for every theta. So what I do is I construct delta 2x, another estimator, which is the mean of delta naught x and delta 1x. Now what I do is I consider the risk of R theta delta 2, which is expected value of under theta of L theta A. So L theta delta naught x plus delta 1x by 2. First note that this loss function L theta A is convex in A. Now if L theta A is convex in A, what does that mean? L theta of alpha A1 plus 1 minus alpha A2, just the definition of a convexity, would always be less than or equal to alpha times L theta A1 plus 1 minus alpha times L theta A2, because it is convex in L theta A is convex in A. Exactly same thing is happening over here, except that alpha is half. So, this quantity would always be less than or equal to half times L theta delta naught plus half times L theta delta 1 x for any x. So, the expectation you know that preserves the inequality. If h1x is less than or equal to h2y, then expected value of h1x would be less than or equal to expected value of h2y. So, this would always be less than or equal to expected value of half of L theta delta naught x plus half times L theta delta 1 x, which is r theta delta naught, expect to this because r theta delta naught by 2 plus r theta delta 1 by 2. What does that mean? So, suprema over r theta delta naught 1 and r theta delta 1. But we have seen that this is what does this condition implies? This condition implies that r theta delta naught is always less than or equal to r naught. In fact, it is exactly same as r naught. And this condition implies that r theta delta 1 would always be less than or equal to r naught for every theta. So, this is always less than or equal to r naught plus r naught by 2 for every theta belonging to theta. So, what does that mean? That means r theta delta 2 is less than or equal to r naught, which is same as r theta delta naught for every theta. And since your when will you have equality? With equality, in fact, loss function is given to be strictly convex. So, there will be strict inequality over here because loss function is given to be strictly convex. So, unless delta 2 is same as delta naught and delta 1 by 2 almost surely. So, this would always be less than or equal to r theta delta naught. Right. So, if I slightly modify my statements here, let delta naught and delta 1 be two estimators which are not identical. So, such that delta naught is not equal to delta 1 or delta naught is equal to delta 1 is less than 1 for every theta. So, that means they are not same almost surely. Then suddenly delta 2 would be different from delta naught. And that is why you will have a strict inequality over here. Now, if this happens, delta naught is given to be admissible, and then you have found an estimator whose risk is smaller than the risk of delta naught. So, this proves that delta naught is inadmissible, which is a contradiction. Right. So, very quite useful result, simple to prove. What it says is, if you have an admissible estimator which has a constant risk, that will always be minimax. Not only that, if your loss function is strictly convex, then an admissible estimator with constant risk would be unique minimax. So, this was the discussion about minimaxity, Bayesian. So, what I will do is in the next lecture, I will consider these. So, what we did in the last few lectures is we studied the Bayes and minimaxity for estimators. Now, one can talk about Bayes and minimax decision rules. For example, estimators are particular kind of decision rules. So, one can talk about the concept of Bayes decision rules, one can talk the concept of a Minimax decision rules. So what I'll do in the next lecture is, I'll give a decision theoretic formulation of a 2-action problems. So that means any decision problem where one is faced with a problem of taking only 2 actions. As it happens in the testing of hypothesis. You have a null hypothesis, you have alternative hypothesis. So the usual problem is either to accept null hypothesis or to accept alternative hypothesis. So that's 2 possible actions. So I'll do a formulation of a decision problem which has only 2 possible actions. So in particular, that formulation would cover the testing of hypothesis problem. So, but that would be for the next lecture. That's all for today. Thank you very much.